Hello again, algebra students. Welcome back to day 2 of exponential growth and decay. We are on page 621, picking up where we left off yesterday. Hopefully you've already gone back and checked your answers against the answer key from last night's homework. If you're struggling, make sure you go back and rewatch the videos, talk to your neighbor. You can visit Coach Russell for tutorials if need be. Today we're going to talk about exponential decay, and we kind of touched on it yesterday that the main difference here is that our growth rate is going to be less than 1. And so that with A is still the initial value, is still greater than 0. B has to be less than 1 this time, but greater than 0. We can't have a negative growth rate. Instead, we have, like if you think about it, if we were to multiply by a negative growth rate, we're then zigzagging back and forth across the y-axis. So in order to show that something is decreasing in value or decreasing over time, we multiply by something smaller than 1, which is like multiplying by a fraction or a decimal smaller than 1. And like we mentioned yesterday, multiplying by a fraction is the same as dividing. So we're making our value smaller and smaller and smaller by continually multiplying by a number that's less than 1. So that's where you see right here our b value is 1 minus r. Okay, so here's our exponential decay function. The only change here is the subtraction. So it's the same as yesterday. A is the initial value, and this time we call this 1 minus r the decay factor instead of the growth factor. But r is still the rate, which is going to be a percentage that we need to change to a decimal, and t is still the time. So let's take what we learned yesterday, where we left off, and see if we can go ahead and jump into writing the exponential function for this decay. Exponential decay. So again, when you're reading these problem situations, you will need to be able to identify whether it's an exponential growth problem or an exponential decay problem. And so the wording in the problems is a dead giveaway. So the population of a town is decreasing. That means that this is a decay question. So we would expect our graph to look, going down somewhere. This or this. These are both decay graph shapes. Okay, so we have a rate of 3%, which is 0.03. We have, in 2005, there were 1,600 people. So this is our initial value. This is A, and that's where we're starting, 2005. We're looking for find the population in 2013. So they got a little tricky on this one. Instead of just telling you the time, we're going to actually have to calculate it. It's not difficult, but just something to pay attention to. So if we're going from 2005, that would be year 0, our initial amount, to 2013, that would be 8 years. So our time is 8 years. So write the exponential decay function for this situation. Here is the exponential decay function formula, and they plugged in what we knew. So we have A is 1,600. They did 1 minus our rate. That's going to cause us to be multiplying by something smaller than 1 here, the 0.97. And then this is the rule for this function. Okay, so if you were graphing, this is what you would put in. All right. Now down here, we are actually using the function in order to answer the question. If you were just asked to graph the function or show the shape of the graph and wanted to plug it into the y equals screen of your calculator, this is what you would put in. And again, that t is the independent variable, so you would replace it with x in your calculator. But we actually want to use the function to figure out after 8 years what is the town's population. So we'd plug it in the calculator, 1,600 times 0.97 to the power of 8, and we get the same thing that they got here. Obviously, for a population, you have to round to the nearest whole person because we don't want any half or quarter people running around, just arms and legs. That'd be kind of weird. So we need entire people. So after 8 years, the town's population is about 1,254 people. So let's give it a try. Let's do part B on page 622. The value of the car is depreciating. That's a vocabulary word. Depreciating means losing value. By the way, when you purchase a brand new car, it immediately depreciates as soon as you drive it off of the car lot. So the value of a car is depreciating, so decaying, at a rate of 5% per year. So our rate is 0.05. Again, be really careful when you're changing those percentages, single-digit percentages, to a decimal. In 2010, the car was worth $32,000, so that's our initial value. Find the value of the car in 2013. Well, how much time has passed between 2010 and 2013? That would be 3 years. So let's plug in everything we know. Let's write our function. We have A, 32,000 is where we're starting, and we're going to multiply by 1 minus 0.05, which is 0.95. So 32,000, we're getting 95% of our value every year. So 95% this year is going to be more than 95% next year. It's always decreasing. It's kind of like your car going on sale every single year, except not to buy, but if you were to sell it. Find the value in 3 years. So again, 32,000. You guys know how I love this book and how many times it repeats the same thing. To the power of t, 0.95. Plug it in my calculator. 32,000 times 0.95 to the third power, and I get 27,436. So after 3 years, the car's value is $27,436. Now, if we bought this car for $32,000, this is just some real world life lessons here. You bought a car for $32,000. Most car loans take anywhere from 3 to 6 years to pay off. Well, if you, depending on your interest rate and how many payments you're planning to make, how long you extended the loan for, if after 3 years your car's only worth $27,000, if you're trying to sell it, you're not going to get, you've lost about $5,000 of what you've spent. And so if you haven't made more than $5,000 of payments at that point, in other words, if you owe more than this after that 3 years, then you're what we call upside down. And then it becomes a very difficult financial hole to dig yourself out of, but not impossible, just something to watch out for. So you would like, in an ideal world, you want to be paying off your car faster than it's depreciating. So same with a house, same with anything that you're trying to sell. All right, if we create our table, let's see, I can go to my table here. I've got to put in my function first though. Oh my goodness. 32,000, remember we're going to leave the t as time, we'll enter in this function here, times 0.95 to the power of x. Now I can go look at the table and get all of these values. So at 0 years, the car is worth 32,000. That's the initial value. After 1 year, it's down to only $30,400. After 2 years, $28,880. 3 years, $27,436. And so I'm just going to go take a quick peek at my graph. It's not set for the right window. Now, if you're trying to adjust the window on your own, they don't tell you how to adjust the window. Just think about what your items mean here. So the smallest x that I have is 0. The largest x that I have, we'll go up to like 10 years. And we'll go up by 1 at a time. That's the x scale. The y's need to start at about, well, we can start y at 0. It's not going to go below 0, we know that. The car's not going to be worth negative value. It might be worth nothing or really close to nothing, but not negative numbers. And our max, 32,000 is our max because that's what we're starting with and it's depreciating. And let's just say, let's do a scale of 4,000. So each line on the graph would be 4,000. That's what they have here. So now if I go look at my graph, I get a clearer picture. It's not super steep decline, that's okay. But you know, it is declining. It's depreciating. So kind of like this. The domain here, domain and range are a big deal. Domain is all real numbers as long as t is greater than 0. Again, That's t is time, x is time. We can't go back in time. And you're going to find that the domain will typically be whatever your independent variable is got to be greater than 1. All real numbers greater than 1. If your